Hey everybody, welcome back. In the previous three videos, we covered the module 4, 5, and 6 parts of the study guide for the final exam. In this video, we're going to be covering module 7, which is the last module that covers questions 33 through 44. So module 7 starts off talking about what's called Pearson's R value. And so each of these R values we need to describe what type of a correlation it is based on the R value. And the R value scale looks like this. Zero's in the middle, and then it goes as far as 1 on the right or -1 on the left. On the right side, we have what would be a strong positive correlation, meaning the two variables that we're investigating are closely correlated with each other. So the further on the right, this R value is on this scale, the closer to 1 it is, the stronger and more positive the relationship is. If we're in the middle, there's a weak or a no pattern type of a relationship. There's not much of a correlation between the two variables we're investigating. And then on the very left, we have a strong negative correlation. So looking at each of the parts for A, B, C, and D, if we were to place those R values on the number line, we would be able to tell what type of a correlation it is. So for part A, for example, 0.95 is all the way on the right side there. So this would be a strong positive since it's all the way on the right. Looks like B is 0.14, so it's probably closer to the middle. That's a weak relationship. It's on the right side. We're gonna call it a weak positive relationship. Negative 0.25 is on the left, still close to the middle though. So that's a weak, but since it's negative, we put a negative, weak negative. And lastly, part D says negative 0.91. So it's all the way close to the left side. It's pretty close to it. So this would be a weak, sorry, not weak, strong, but negative. So identifying the type of relationship is based upon that number line across at the top. 34 says if a correlation between two variables is positive, what relationship do the variables have as they change? So this is what a positive relationship looks like in terms of statistics and two variables. You line them up on the x and y axis. And if it's saying that the two variables, so the two variables refer to whatever's being measured on the x-axis, whatever's being measured on the y-axis, if their relationship is positive, that means that the dots have an upwards trend, something like that. And the closer the dots are to a straight line, the stronger the relationship is. So what's happening to these two variables separately is, in this case, if you have a positive relationship, that means as x increases, y also increases, meaning as I go further out on the x-axis, I'm also increasing myself or increasing the value on the y-axis. That's why it's going upwards in this direction, is because I'm moving outward on the x. I'm also moving outwards or upwards on the y-axis. If a correlation between two variables is negative, what does that look like and what relationship do the variables have? So similar idea, we're still going to draw on our xy axis like this, but a negative relationship looks like this. The dots are downwards trending, and they don't always end up in a perfect line, but you can see the trend is going downwards. So in this case, the way we would phrase it is as x increases, meaning as I walk, if somebody were to walk on this x axis going towards the right, if I were getting increasing on my x axis, it looks like the dots are moving closer downwards on the y axis. And I would say as x increases, y decreases. The values on your y scale are going down as you're going upwards this way. What are interpolation and extrapolation? These are two vocab words that we talked about in the notes, and they represent different types of regression. Interpolation, and I'll just write the letter I for interpolation and E for extrapolation. There's a full definition in the solution key towards the back that you can read out entirely, but in short, interpolation is predicting, sorry, let me redo that. Within a known X variable range, I'm just calling it X range, predicting within a known X variable range. And extrapolation is the same thing, but predicting outside of the known range. So the key idea here is interpolation is within or inside, extrapolation is outside of a range, outside. And so this next example will make sense, will make this part make more sense. Number 37 says that we have a situation where our height of elementary school kids is the y variable and age is x. So we're looking at the relationship between height and age. Which of the following situations is appropriate to use for this model? Appropriate means interpolation. You're predicting within the known range. The known range would be elementary school kids. So here it looks like second grade and fifth grade are both within the known range of our demographic, elementary school kids. So second grader, that would be interpolation. And fifth grader would be interpolation because second and fifth grade falls within elementary school age. However, ninth grade and 10th grade, ninth grade and adults, that would be considered extrapolation. I'm putting E for extrapolation because as we age, our height isn't necessarily based on our age anymore. Once we reach a certain age in life, we don't keep growing until we become like forever. We our growth slows down, but in our earlier ages in elementary school, our growth probably does match up with our age a little bit. So that's why extrapolation has to do with you're trying to apply one rule or one pattern outside of the range where it doesn't work anymore. So that's why extrapolation would be the grades or ages that are outside of the elementary school range. 38 also illustrates this same idea. It says if the X values we collect are on the range from 50 to 75, for example, which of the following represents interpolation and which ones represent extrapolation? So interpolation would be anything inside of this range, 50 to 75. So it looks like 54 and 72 are within the range. So those are examples of interpolation, whereas 32 and 95 are extrapolation because they are outside of the 50 to 75 range. 39 and 40 are asking you to use what's called a regression model. A regression model is basically a equation that represents a line. And those lines represent a pattern that might illustrate a certain situation or a relationship between two variables. So the regression model uses X and Y variables, and it also has what we call a slope and y-intercept, which probably you're sounding familiar from a previous math class that you may have taken. It says predict values of y if x are each of the following. So if we have our model or our equation, we're going to plug in these are x values, and we're going to plug them in to x and figure out what y is. So all we're doing is saying for part A, for example, y equals 3.52. Instead of x, we're going to put times 10. Take part A and then subtract 12. So this isn't a multiple choice question in the review. This is 3 different practice examples to do. Plug in a 10 Then the next time plug in 15 for B, for C plug in a 4, and determine what this would all equal out to, punch it into your calculator. So I won't do all the parts, you can practice that on your own, but when you calculate this, you should end up for part A. Just to make sure that you're on the right track, this should be a 23.2. So likewise, do parts B and C and practice those, and you can compare with the key. Number 40, also same idea. It gives you your regression model right there. It's kind of overlapped onto two lines, y equals. And we're doing the same thing here. Take your x values and plug them in. So for part A, for example, y equals 0.813 times, in this case, we're measuring the kilogram weight of the patient to determine their metabolic rate, plus 0.14. So crunch those numbers in the calculator. What you should get for part A, to make sure that you're doing this correctly, you should get 16.40. Do the same things for part B and C on each of these. Let's keep going. Numbers 41 through 44 talk about doing what's called an ANOVA test. And in an ANOVA test, it's kind of like a hypothesis test. You do have a null and alternative hypothesis. So H0 and HA or H1, depending on what it says in the problem, but null and alternative. In an ANOVA test, you have several means, not just one. You have more than one. So in an ANOVA test, the null hypothesis will say that all means are equal, because before we would say mu equals some number for the null hypothesis. But when you have multiple, you would say mu1 equals mu2 equals mu3 equals so on and so forth. If you have an ANOVA test, you have several um, averages or several population means. So in short, you can put all means are equal. For the alternative test, these symbols might have any different combination, but the most basic one is at least one mean is different. So basically, you're just taking the most simplest form, putting a not equals in between there. But in words is usually how the null and alternative are written. All the means are equal for the null. At least one mean is different for the alternative. For the assumptions, you're going to want to take a look in your answer key towards the back of the packet to see what the different assumptions are. I believe there are 3 or 4. Just make sure you look at those and read those assumptions for the ANOVA test. For number 43 and 44, you're given what's called an ANOVA table, analysis of variance. Those letters actually, ANOVA is hidden in there, ANOVA. Analysis of variance, it will give you this table right here in the problem, and it will ask you one of these possible questions. And so all we have to do is determine which value goes with which box. So the row that says between, or sorry, the row that says treatments is the row that refers to anything that would be what we would consider between. And then the row that says error is called the within row. So for example, on part A, it says SSTOT. That's actually written like this, SS, and then the TOT is kind of small, and it stands for total, actually. And so the total, you notice there's a total row as well. So SSTOT goes with the sum of squares. The S and the S stand for sum of squares. So sum of squares total, you'd match up that row and column, and there it is. There's your SS total. 663.14. And of course, there's more decimals there, but I'll just leave it at that. SS between looks like this. capital S, and then the BET are smaller, representing between. And so the treatments row is the between row. We're looking at sum of squares, SS. So let me actually write that up here. SS. This one over here is MS. Yeah. So SS between, we got match up the sum of squares row. The between is the first one, the treatments, that's 134. And of course, there's more decimals, but I'm just going to leave it at 2 for now. And then SSW, that's SS within. Capital S, small w. So sum of squares within, that's the second row right there, 529.14. So not really any calculating to be done here. All we're doing is just finding the numbers in the boxes. We got what is DF between? And this one's written like this, similar to before. But now instead of the SS column, we're looking at the degrees of freedom column. This one right here, DF. So DF between looks like it's 2. DFW, so degrees of freedom within, looks like it's this column, this row, so that's an 18. What's the F statistic? That's really easy, just the number up here for the F statistic, and then what's the p-value? There it is right there. So those two last numbers are important, and all you have to do is locate them. So our F statistic is 2.279, and there's of course more digits. On the final exam, your answer choices will have a set number of decimals in there so you can see your answer choices and know how many decimals to round to. Our p-value here is going to be 0.13. Of course, there's more. We'll leave it at that. And then the last part here says if we test at an alpha equals 0.05 level, what would our conclusion be? We're going to use the same principles we used for the previous chapters of hypothesis testing to compare P and alpha. So for this particular part right here, our alpha is 0.05 and our P is 0.13. So we got 0.13, 0.05, and I need to think about, okay, so that's P, that's alpha. The symbol that needs to go in between them looks like it would be a greater than symbol because 0.13 is greater than 0.05. The one that's greater than is the P. So this leads us to make the conclusion we fail to reject H0. And this comes from what we talked about in the previous video in Module 6, which is right here. In Module 6, sorry, apologize, Module 5. Module 5, these were our two conclusions. P is less than alpha, P is greater than alpha. So we just got that P is greater than alpha, that's what we failed to reject. If P was less than alpha, we would reject the null hypothesis. Number 44 is just another example practicing the same thing. You can test out all these other ones. For the very last part though, comparing this p-value with our alpha of 0.10, I'm just going to work that part out here because I assume that you can figure out and determine where these are in the table. But for this last one here, it says, so we got a p-value of 0.0000. There's a lot of zeros in there. 1, 2, 3, 4. And there's a 4. And then our alpha is 0.10. So it looks like we would put a less than symbol here. E is less than alpha. So we would reject H0. There you go. Okay, so that covers the entirety of Module 7. And remember that there's a video for every single module in the review packet. So be sure to look through each one separately to focus in and study on what you need to. And of course, if you have questions, please feel free to reach out to me. And then if you want to, please stop by office hours to ask me any clarifying questions that I can further explain.